Imagine building something so massive, it feels like constructing the spine of a giant. A structure where multi-ton steel and concrete box girders are lifted hundreds of feet into the air, perfectly aligned and connected with millimeter precision. Now imagine doing this above a powerful tidal river where wind loads, navigation clearance, and geological constraints make construction incredibly complex. How do engineers assemble such gigantic structural components high above the ground? How do they maintain stability, balance, and strength while the structure is still incomplete? And how does this enormous spine carry thousands of vehicles every single day, safely transferring loads across a vast river channel? This isn't just a bridge. This is one of the most fascinating structural achievements in modern bridge engineering. Today, we uncover the engineering secrets behind the Penobscot Narrows Bridge, a masterpiece where box girder technology, cable stay design, and precision construction come together to create one of the most unique bridges ever built. Welcome to Civil Engineering Edge, the channel where we explore the science, technology, and real-world engineering behind the world's most incredible infrastructure. From towering skyscrapers to record-breaking bridges, from advanced construction techniques to revolutionary structural systems, this channel is dedicated to civil engineers, engineering students, and anyone passionate about how the world is built. Every bridge, tunnel, and skyscraper we see around us is more than just concrete and steel. Behind every structure lies careful design calculations, complex load analysis, innovative construction methods, and bold engineering decisions. And today's project is one of those masterpieces. A bridge that stretches across the Penobscot River, designed not only to handle immense structural loads, but also to survive harsh coastal weather, strong winds, and decades of service life. In this video, we will explore the Penobscot Narrows Bridge, focusing on the incredible box girder system that forms its backbone. We'll break down the design philosophy, structural behavior, construction challenges, and engineering innovations that made this project possible. So whether you're a professional civil engineer, a structural designer, or a curious engineering student, this video will give you a deep insight into one of the most fascinating bridge structures in the world. Let's begin. Engineering an icon, dramatic opening shot, the monumental scale. As the camera rises above the coastline of Maine, a magnificent structure appears across the Penobscot River. Stretching across the water with elegance and power stands the Penobscot Narrows Bridge, one of the most visually striking bridges in North America. Completed in 2006, this cable-stayed bridge replaced the aging Waldo-Hancock Bridge, which had served the region for nearly 70 years. But the new bridge wasn't just a replacement. It was designed to become an engineering landmark. The bridge towers soar more than 130 meters above the river, supporting a network of steel cables that radiate outward like the strings of a giant musical instrument. Below these cables lies the true backbone of the structure, the box girder deck, a massive structural element carrying traffic across the river. The bridge spans approximately 2,120 feet, connecting the towns of Prospect and Verona Island. Thousands of vehicles cross this structure every day. But what most drivers never realize is that beneath the roadway lies a highly sophisticated structural system designed to resist bending, torsion, dynamic traffic loads, wind forces, and seismic activity. The bridge must withstand not only the weight of vehicles, but also temperature changes, tidal river currents, strong Atlantic winds, and decades of structural fatigue. To achieve this, engineers relied on a combination of cable-stayed technology and steel box girder construction, creating a bridge that is both strong and lightweight. This combination allows the bridge to maintain exceptional stiffness while efficiently distributing loads from the deck to the towers and foundations. But the most fascinating part lies within the structure itself, the hidden engineering that makes the entire bridge behave like a single unified spine. The giant spine metaphor. Think of the bridge deck as the spine of a gigantic creature stretching across the river. Just like the spine in the human body supports the skeleton, the box girder structure supports the entire bridge deck. A box girder is a hollow structural beam, typically made from steel or reinforced concrete, shaped like a rectangular or trapezoidal box. This closed shape provides extraordinary resistance to bending and torsional forces. In simple terms, a box girder behaves like a structural tube. Because the section is enclosed, it can resist twisting forces far better than traditional I-beam girders. This is extremely important in long-span bridges where wind, asymmetric traffic loads, and cable forces can create complex torsional stresses. Inside the Penobscot Narrows Bridge, these massive box girders act as the central structural backbone. They carry loads from the roadway and transfer them through the cable system into the bridge towers. Each section of the box girder must be fabricated with precise geometry and tight tolerances, because even a few millimeters of misalignment could affect the structural integrity of the entire span. During construction, these box girder segments were fabricated off-site and transported to the bridge location. Each segment weighed several tons. Engineers then used powerful lifting systems and cranes to position them accurately between the bridge towers. Once installed, the segments were welded and connected together, gradually forming the continuous spinal structure of the bridge deck. As more segments were added, the bridge slowly extended outward across the river, much like the vertebrae of a spine growing one by one. The engineering challenge: building without traditional methods. Constructing a bridge of this scale presents enormous challenges, but the location of the Penobscot Narrows Bridge made the project even more complex. The bridge had to be built across a busy navigational river channel, where large ships and vessels regularly pass through. This meant engineers could not simply construct large temporary scaffolding or support structures across the river. Traditional falsework construction methods were impossible. Instead, engineers had to rely on a highly advanced technique known as balanced cantilever construction. In this method, bridge segments are installed outward from the main towers in a carefully balanced sequence. A segment is placed on one side of the tower, and then another segment is placed on the opposite side. This keeps the structure balanced and prevents dangerous bending moments during construction. Specialized segment lifting cranes, mounted on the partially completed bridge deck, were used to lift each box girder section into position. As each segment was installed, stay cables were attached to support the growing structure. These cables temporarily carried the loads until the entire bridge deck was completed. The process required extreme precision. Engineers constantly monitored structural deflection, cable tension forces, wind effects, and alignment accuracy. Even temperature changes could cause the steel structure to expand or contract, affecting the installation process. Yet, through meticulous planning, advanced structural analysis, and cutting-edge construction technology, engineers successfully assembled this enormous bridge hundreds of feet above the river. The result is a structure that appears graceful and effortless from afar, but is, in reality, an incredible masterpiece of modern civil engineering. The box girder revelation. Transition to the core engineering concept, the box girder. Now that we've seen the monumental scale of the Penobscot Narrows Bridge, it's time to focus on the true structural backbone that makes this bridge possible, the box girder. At first glance, the bridge deck may look like a simple roadway suspended by cables. But beneath that roadway lies a highly engineered structural system designed to handle enormous forces. So what exactly is a box girder? A box girder is a hollow structural beam typically made from steel, reinforced concrete, or press-dressed concrete, shaped like a rectangular or trapezoidal box. Unlike traditional beams that have open cross-sections, a box girder forms a closed tubular structure. This closed geometry dramatically increases the beam's ability to resist bending and twisting forces. To understand why this is revolutionary for long-span bridges, we need to consider the loads acting on a bridge deck. Every bridge must carry dead loads, the weight of the structure itself, live loads, vehicles, and traffic. Dynamic loads, vibrations from moving vehicles. Wind loads, lateral forces acting on the deck. Torsional loads, twisting forces caused by uneven traffic or wind. In long-span bridges like the Penobscot Narrows Bridge, these loads become extremely complex. A traditional open girder system would struggle to resist the torsional forces created by cable-stayed designs. This is where the box girder becomes essential. Because the cross-section forms a closed structural loop, it provides exceptional torsional rigidity. This means the structure resists twisting much more effectively than conventional beam systems. For cable-stayed bridges, this stiffness is critical because the deck must remain stable while cables transfer loads to the towers. In simple terms, the box girder allows engineers to create a longer, stronger, and lighter bridge deck, making modern long-span bridge construction possible. Internal structure of a box girder. To truly appreciate the engineering brilliance of box girders, we need to look inside the structure itself. Imagine slicing the bridge deck and looking at its cross-section. Instead of a solid block of steel or concrete, you would see a hollow chamber surrounded by thick structural plates. This chamber forms the box section. Inside the box girder are several important structural components that work together to maintain strength and stability. First, we have the top flange. This is the upper plate of the box girder and forms part of the bridge deck that directly supports the roadway slab. Next comes the bottom flange. This plate forms the underside of the girder and carries tensile forces created by bending. Connecting the top and bottom flanges are the web plates, which form the vertical sides of the box. These web plates transfer shear forces between the top and bottom flanges. Inside the hollow chamber, engineers often install internal stiffeners and diaphragms. These components serve several important purposes. They prevent the plates from buckling under compressive forces. They distribute loads across the structure. They maintain the geometric stability of the girder. They improve resistance to torsion and shear forces. Because the structure is hollow, it uses far less material than a solid beam, while still maintaining incredible strength. This results in an outstanding strength-to-weight ratio. In structural engineering, this is a major advantage. A lighter structure reduces loads on foundations, towers, and cables, while still maintaining high load-bearing capacity. This is exactly why box girders are widely used in modern cable-stayed bridges, long-span bridges, and curved bridge decks. The design combines efficiency, strength, and stability in a way that few other structural systems can achieve. Comparison with older bridge construction systems. To understand why box girders are such a breakthrough in bridge engineering, it helps to compare them with older bridge construction systems. For decades, most bridges were built using I-girders, trusses, or beam and slab systems. Each of these systems had its advantages, but they also came with limitations. Let's start with I-girder bridges. I-girders consist of a vertical web with horizontal flanges at the top and bottom, forming an I shape. These beams are excellent at resisting vertical bending forces. However, their open cross-section makes them less resistant to torsion. If uneven loads act on the deck, for example, heavy vehicles traveling on one side, the girder can experience twisting. This limitation becomes more critical as bridge spans increase. Next are truss bridges, which use a network of triangular steel members to distribute loads. Truss systems are strong and efficient for moderate spans, but they require large amounts of steel, extensive maintenance, and complex fabrication. They are also visually heavy and can obstruct views, which is not ideal for modern infrastructure design. Beam and slab bridges, commonly used for short spans, rely on reinforced concrete beams supporting a slab. While economical for smaller bridges, they become inefficient and heavy for long spans. Now compare these systems to box girders. Box girders offer several key advantages: superior torsional resistance, higher structural efficiency, reduced material usage, greater stability under asymmetric loading, better performance in curved bridges, sleeker architectural appearance, In cable-stayed bridges like the Penobscot Narrows Bridge, these benefits become even more important. Because the stay cables apply forces at different points along the deck, the bridge structure must resist complex bending and twisting forces simultaneously. A box girder system handles these forces elegantly, acting as a continuous structural spine that stabilizes the entire bridge. This is why many of the world's most advanced bridges today rely on box girder technology, a perfect blend of strength, efficiency, and modern engineering innovation. Overcoming nature's fury, environmental challenges at the Penobscot Narrows. Building a bridge across a river is always a challenge. But constructing a major cable-stayed bridge across the Penobscot River in the town of Prospect, in the state of Maine, presented engineers with a unique combination of environmental obstacles. The location is known as the Penobscot Narrows, a narrow section of the river where water flows between steep banks before opening into the bay. While the narrow width is helpful for bridge span design, it also creates powerful tidal currents that move enormous volumes of water through the channel every day. Unlike calm inland rivers, this section of the Penobscot experiences strong tidal fluctuations, where water levels can rise and fall significantly within a short period of time. These tidal movements create fast-moving currents and turbulent flow patterns around the bridge foundations. Such hydraulic conditions make it extremely difficult to install traditional construction supports like temporary falsework or scaffolding in the water. Another challenge was the deep navigation channel. The river serves as an important route for vessels traveling to inland ports, meaning engineers had to maintain a wide and unobstructed waterway for ships passing beneath the bridge. This restricted the number and placement of piers that could be built within the river itself. On top of that, the coastal environment of Maine introduces harsh weather conditions. The bridge site regularly experiences strong coastal winds, freezing winter temperatures, ice accumulation, storm-driven waves, and rain. These environmental factors create enormous stresses on any structure built in the area. For engineers designing the Penobscot Narrows Bridge and Observatory, the challenge was clear. They needed to create a bridge that could survive powerful natural forces for decades, while also allowing construction to take place safely in such a demanding environment. How box girder design helped overcome these challenges? To successfully overcome these environmental challenges, engineers needed a structural system that was not only strong, but also stable, lightweight, and resistant to twisting forces. This is where the box girder deck played a crucial role. In cable-stayed bridges like the Penobscot Narrows Bridge and Observatory, loads from the roadway are transferred through stay cables into the towers. However, these cables apply forces at multiple points along the bridge deck, creating complex stress patterns. These forces include vertical bending loads, horizontal wind forces, torsional forces caused by uneven traffic or wind pressure. A conventional open girder system would struggle to resist these combined forces efficiently. But a box girder deck behaves like a rigid structural tube. Its closed cross-section provides exceptional torsional stiffness, meaning the bridge can resist twisting caused by wind or uneven loading. This was particularly important in the Penobscot Narrows location, where strong coastal winds regularly push against the bridge deck. The hollow box structure also provides excellent aerodynamic performance. When wind flows around the bridge, the streamlined deck shape helps reduce turbulence and vortex shedding to phenomena that can cause dangerous structural vibrations. Another advantage is structural efficiency. Because box girders use material more efficiently, the overall deck weight becomes lighter. A lighter deck reduces the forces acting on bridge towers, stay cables, foundations. This is extremely beneficial when constructing a bridge in deep water where foundation work is difficult. In essence, the box girder deck acts as a rigid, lightweight spine capable of distributing loads evenly across the entire structure. This allowed engineers to create a bridge that is not only visually elegant, but also capable of resisting powerful environmental forces throughout its service life. prefabrication, and segmental assembly techniques. Even with the right structural design, constructing such a massive bridge in this environment required advanced construction strategies. One of the most important techniques used in the construction of the Penobscot Narrows Bridge and Observatory was segmental construction combined with off-site prefabrication. Instead of building the entire bridge deck piece by piece at the site, engineers divided the box girder structure into large prefabricated segments. Each segment was manufactured in specialized fabrication facilities where engineers could maintain strict quality control. Fabricating these segments in a controlled environment offered several advantages: higher precision in welding and fabrication, improved material quality control, reduced exposure of workers to dangerous weather conditions, faster overall construction time. Once fabricated, the massive steel box girder sections were transported to the bridge site using heavy transport systems. At the construction location, engineers used powerful segment lifting cranes mounted on the partially completed structure. These cranes carefully lifted each prefabricated segment into position. The construction followed a method called balanced cantilever construction. In this technique, segments are added symmetrically on both sides of the bridge towers. This keeps the structure balanced and prevents excessive bending forces during construction. As each segment was installed, stay cables were attached to support the new portion of the deck. The process continued step by step, with the bridge gradually extending outward from the towers toward the center of the river. Because most of the structural work was performed through prefabricated components, engineers minimized the need for large equipment or scaffolding in the river. This significantly reduced the risks associated with deep water construction and strong currents. Through a combination of advanced engineering design, precision fabrication, and innovative construction techniques, engineers were able to assemble a bridge that stands today as one of the most remarkable infrastructure achievements in North America. A towering achievement, the iconic observation tower and its integration with the bridge. When most people think of a bridge, they imagine a structure designed purely for transportation, a pathway connecting to places across water or land. But the Penobscot Narrows Bridge and Observatory offers something extraordinary that very few bridges in the world can claim. It doesn't just carry vehicles across the river, it also allows people to climb inside the bridge itself. Rising dramatically above the Penobscot River is a slender concrete tower that supports the cable-stayed structure. But inside this tower lies a remarkable feature, a public observation deck located approximately 420 feet, 128 meters above the ground. This observatory makes the bridge one of the only bridges in the world with a public viewing tower integrated directly into its structural pylon. Visitors can take an elevator up through the interior of the tower, traveling inside the very structure that holds the bridge together. When they reach the top, they are rewarded with breathtaking panoramic views of the surrounding landscape, including the winding Penobscot River, nearby coastal forests, and the historic Fort Knox, a 19th century granite fort located beside the bridge. From an engineering perspective, integrating an observation deck into a working bridge tower is extremely complex. The tower must not only support thousands of tons of structural loads from the bridge deck and cables, but it must also safely accommodate visitors, elevators, mechanical systems, and viewing platforms. Engineers had to carefully design the tower so that the public space and structural system coexist without compromising safety or performance. The result is a rare blend of infrastructure and tourism, where a critical piece of transportation engineering also becomes a unique architectural landmark. Structural role of the tower and its interaction with the box girders. While the observation deck attracts visitors and photographers, the true purpose of the tower is far more critical. The tower functions as the primary load-bearing element of the cable-stayed bridge system. In the Penobscot Narrows Bridge and Observatory, the central tower rises high above the deck and anchors an array of steel stay cables that extend down to the bridge deck on both sides. These cables form a fan-like pattern, transferring loads between the bridge deck and the tower. To understand this interaction, imagine the bridge deck formed by the steel box girder as the horizontal spine of the structure. The tower acts like the vertical backbone, while the cables behave like tension tendons connecting the two. Here is how the structural load path works. 1. Vehicles and traffic create loads on the roadway deck. 2. These loads are carried by the box girder deck structure. 3. The deck transfers these loads into the stay cables attached at multiple points. 4. The cables carry the forces upward into the tower. 5. Finally, the tower transfers the loads downward into the deep foundations embedded in the riverbed. Because the cables support the deck from above, the bridge can achieve long spans with fewer piers in the water. This design reduces obstruction to navigation and minimizes environmental impact on the river. The tower must therefore resist several types of forces simultaneously. Vertical compression from cable forces, horizontal forces from wind and cable tension, bending moments caused by uneven loading on the deck. The box girder deck plays a crucial role in stabilizing this system. Its high torsional stiffness prevents the deck from twisting under uneven loads, allowing the cable tower system to function efficiently. Together, the tower and box girder deck create a balanced structural system where tension and compression work together to maintain stability. A fascinating story behind the tower. Beyond its impressive engineering, the tower of the Penobscot Narrows Bridge and Observatory also holds an important cultural and historical significance for the local community. The bridge was built to replace the aging Waldo-Hancock Bridge, which had served the region since 1931. By the early 2000s, the old suspension bridge had deteriorated significantly and could no longer safely handle modern traffic loads. Local residents, however, had strong emotional ties to the original bridge. It had been a symbol of connection between communities along the Penobscot River for generations. When plans for the new bridge were developed, engineers and planners wanted to ensure that the new structure would not only improve transportation, but also become a landmark for the region. That's when the idea of a bridge observatory was introduced. Instead of building a tower that served only a structural function, designers decided to create a tower that would also allow people to experience the bridge from inside the structure itself. When the observatory opened in 2007, it immediately became a popular attraction. Visitors could now ride an elevator through the tower and look out from a height higher than the Statue of Liberty's torch level, offering spectacular views of the river valley. For the local community, the tower represents more than engineering. It symbolizes the region's connection to its maritime history, landscape, and modern infrastructure. Today, the bridge is not only a critical transportation link, but also a tourism destination, drawing thousands of visitors every year who come to experience one of the most unique bridge observation towers in the world. Legacy of innovation. Lasting impact of the bridge as a modern engineering achievement. More than just a transportation link, the Penobscot Narrows Bridge and Observatory stands today as a powerful symbol of what modern civil engineering can achieve when innovation meets necessity. Completed in 2006, the bridge represents a turning point in how engineers approach large-scale infrastructure projects in challenging environments. Designed as a cable-stayed bridge with a steel box girder deck, it replaced the aging Waldo-Hancock Bridge, providing a safer, stronger, and far more efficient transportation route across the Penobscot River. But its significance goes far beyond replacing an old bridge. The project demonstrated how advanced structural analysis, precision fabrication, and modern construction techniques could be combined to create infrastructure that is both functional and visually iconic. From the slender cable-stayed tower to the aerodynamically efficient box girder deck, every element of the bridge was designed with long-term durability, safety, and structural efficiency in mind. Engineers carefully analyzed factors such as wind loads, tidal currents, traffic patterns, and seismic stability, ensuring the structure could perform reliably for decades. Perhaps most impressive is how the bridge balances engineering strength with architectural elegance. Unlike older bridges that often appeared bulky or purely utilitarian, the Penobscot Narrows Bridge demonstrates how modern infrastructure can also become a regional landmark and a source of pride for the community. Today, thousands of vehicles cross the bridge every day, often without realizing that they are traveling across one of the most innovative bridge structures ever built in North America. Influence on future infrastructure projects. The engineering strategies used in the Penobscot Narrows Bridge and Observatory have influenced many modern bridge projects around the world. One of the most important contributions of this bridge was the successful application of steel box girder technology combined with cable-stayed structural systems in a challenging coastal environment. This approach demonstrated how engineers could achieve longer spans with fewer support piers, which is especially valuable when building bridges across busy navigation channels or environmentally sensitive waterways. The project also reinforced the advantages of segmental construction and prefabrication techniques. By manufacturing large structural segments in controlled environments and assembling them on site using balanced cantilever methods, engineers were able to significantly improve construction precision, worker safety, and project efficiency. These methods are now widely used in modern bridge construction across the globe. Another influential aspect of the bridge is its multifunctional design philosophy. Traditionally, infrastructure projects focused solely on transportation performance. But the Penobscot Narrows Bridge introduced a concept where a bridge could also serve as a tourism destination and educational landmark. The observation tower integrated into the bridge pylon created a unique opportunity for the public to experience civil engineering up close. This idea has inspired planners and engineers to consider public engagement and architectural aesthetics in many modern infrastructure designs. As cities continue to grow and transportation demands increase, bridges like the Penobscot Narrows Bridge serve as powerful examples of how infrastructure can be efficient, resilient, and visually inspiring at the same time. A powerful closing message: human ingenuity and engineering beauty. When we look at monumental structures like the Penobscot Narrows Bridge and Observatory, we are reminded that engineering is not just about numbers, calculations, and materials. It is about human ingenuity. Every beam, cable, and tower in this bridge represents thousands of hours of design work, simulation, planning, and construction expertise. Civil engineers, structural designers, surveyors, construction workers, and countless specialists collaborated to transform a bold idea into a functioning structure that now serves thousands of people every day. The bridge stands quietly across the Penobscot River, yet it tells an incredible story, a story of innovation, persistence, and creativity. It reminds us that with the right combination of knowledge and determination, humans can build structures that appear to defy gravity itself. From towering skyscrapers to record-breaking bridges, civil engineering continues to shape the world we live in. And bridges like this one prove that infrastructure can be more than just practical. It can also be beautiful, inspiring, and timeless. The next time you cross a bridge or look at a massive structure, remember the hidden science and creativity behind it. Because somewhere, a team of engineers imagined it first. And if you're fascinated by the world of engineering, the structures, the technology, and the ideas that shape our civilization, then stay curious. Here on Civil Engineering Edge, we will continue exploring the most incredible engineering marvels from around the world, because every great structure has a story, and the next one might be even more extraordinary. The best true example of engineering excellence when discussing modern bridge engineering, the Penobscot Narrows Bridge and Observatory stands as a true and inspiring example of how engineering innovation can solve complex real-world challenges. This bridge perfectly demonstrates how different engineering disciplines come together to create a structure that is safe, efficient, durable, and visually striking. From the structural perspective, the bridge showcases the power of box girder technology combined with cable-stayed bridge designs. The box girder deck acts as a rigid spine capable of resisting bending and torsional forces while distributing loads efficiently across the structure. At the same time, the cable-stayed system transfers these loads upward to the towering pylon and down into the deep foundations embedded in the riverbed. But the true brilliance of this project lies in how engineers balanced multiple constraints simultaneously. They had to design a bridge that could withstand strong coastal winds, resist powerful tidal river currents, maintain navigation clearance for ships, replace an aging historic bridge safely, minimize environmental impact on the river, provide long-term durability for decades of service. Despite all these challenges, the final structure remains lightweight, elegant, and structurally efficient. The bridge also represents a perfect example of modern construction strategy. Through prefabrication and segmental erection methods, engineers were able to assemble massive structural components with millimeter-level precision hundreds of feet above the river. For civil engineering students and professionals, this bridge offers a real-world lesson in structural design, construction planning, and interdisciplinary collaboration. It shows how engineering is not simply about building large structures, it is about designing intelligent solutions that respect nature, serve communities, and stand the test of time. In many ways, the Penobscot Narrows Bridge is not just a bridge. It is a living classroom of modern civil engineering. And that brings us to the end of today's exploration of the remarkable Penobscot Narrows Bridge and Observatory, a bridge that truly represents the power of modern civil engineering. From its massive box girder spine to its elegant cable-stayed tower, every part of this structure reflects the creativity, precision, and determination of the engineers who designed and built it. Projects like this remind us that civil engineering is not just about construction. It is about connecting communities, overcoming natural challenges, and shaping the infrastructure of the future. If you enjoyed discovering the engineering secrets behind this incredible bridge, make sure to like the video, share it with fellow engineers and students, and subscribe to Civil Engineering Edge for more deep dives into the world's most fascinating infrastructure projects. Here, we explore the science, design, and construction techniques behind the structures that define our modern world. Until next time, keep learning, keep building, and keep exploring the amazing world of civil engineering.